All right, we're going to look at a Gauss's law problem that has a cylindrical symmetry. So what that's going to mean is there's going to be some like can-shaped or wire-shaped distribution of charge, and it's going to need to be really long in these problems. The idea there is if you make the thing short or have to worry about the ends, then you've kind of ruined the cylindrical symmetry, and so you won't be able to draw the Gaussian surface that you need. So when you see these kind of problems, it's going to be some super long, again, wire-shaped thing. So just to kind of set a context for this, we need to have some kind of, say, a changing charge density in here. So I'll just kind of make one up. Let's suppose that the charge density inside here, the charge per volume, grows like r squared. So we'll say it's some constant, I'll just make one up like capital K times r squared. And we'll say if the charge density is K times r squared, the problem was going to be to find the electric field everywhere. So find E everywhere. Okay, so that's a type of problem that you could get. Well, first of all, you need to know what Gauss's law is. And so Gauss's law, it says that the flux, which is the integral of E dot dA through a closed surface, the flux through a closed surface, equals the charge enclosed over a constant, over epsilon naught. Okay, so this looks fancy. A way that I kind of teach my students is ultimately this boils down to like EA perpendicular. If you are clever enough to find a surface where the E is constant, it will just be field times the area perpendicular to the surface. So let's look at this situation. So what this means is if you have a charge density that's growing like r squared, right? It means in the middle it's relatively uncharged, and then it's going to grow and grow and grow quadratically so that as you get to the outside, there's quite a bit of, say, positive charge here at the outside, at the very edge, out at radius r. So the charge density is just going to grow and grow and grow like a parabola until you get to the outside, and then it's gone after that. Then there isn't any charge, say, on the outside of this thing. So in general, there's going to be like two regimes. There's going to be like what's going on inside the thing, and then what's going on outside the thing. So let's play around with this. So we're going to find E everywhere. So let's look inside, meaning that the distance away from the center, let's say, is going to be less than the radius of the whole thing. So we'll say r less than or equal to big R. So we're going to look inside. So when you go to use Gauss's law, this is the flux through an imaginary Gaussian surface that you make up as a tool for calculating electric field. So we need to make up a Gaussian surface, and you want to choose one that's always perpendicular or parallel to the field, so it's easy to calculate things. So what's going to happen here is in all these problems you need to be able to at least envision the field. So the field's going to just point like away, right? It's just going to point outward in all directions like a bristle brush. So like out here it's going to point this way, this way, this way, away. And so if you want to envision a surface that's going to make things convenient for us, well, it's going to be a cylinder. And so what you do is you draw your what's called a Gaussian surface inside. And what you're going to want to do is make it have a radius little r, and you want it to be kind of a flexible in that you're finding ultimately the field as a function of r. So we'll call this little r. And then we'll give it some kind of a length. So the length is L. We'll just make it up. So this is our imaginary little Gaussian surface that we're going to use as a tool for calculating the electric field. Well, so then we go to use Gauss's law. Integral E dot dA, okay, which is actually, again, you're really the meaning of this integral is just the flux through the surface. So as I mentioned, ultimately, if you're clever about your surface, this boils down to EAperp, E times the area perpendicular to the surface, right? So one way to think about this total flux is you have the flux that's through the end caps, like so here's one end cap and here's the other end cap. So you'd have like the electric flux through the ends plus the flux through like the soup can label, the wall of the cylinder. I'll call it the wall of it. Right, it's a Campbell soup can, and that would be like the label, okay? And so the flux through the end plus the flux through the wall, that's going to be Q enclosed over epsilon naught. Q inc over epsilon naught. Right. Well, the flux to the ends is going to be 0 because the field just points radially away, so none punches through the ends. So there's no flux there. Then the flux through the wall is just going to be the field times the area that you present perpendicular to the field. Well, so you have to imagine cutting this soup can label out, and if you did that, I'll just kind of draw it. It would be shaped like a rectangle, maybe. And you know, how long would this be? Well, that would be the circumference of this circle, so 2 pi r. And then how wide would it be? Why that, whoops, 2 pi r I meant to write. And then this dimension would be L. So that's like if you unwound the soup can label like this, right? So EAperp is going to be E times 2 pi RL. This happens all the time with these Gauss's law problems in cylindrical symmetry. The left-hand side is quite easy because you just use a cylindrical Gaussian surface, and the left-hand side is going to look like this. The labor always comes in on calculating the total charge. So we got 1 over epsilon naught, and then now we're going to get the total charge. So we're going to do a little side project to get this. Now the logic of this is charge is always the sum of the little bits of charge. And so the challenge is always coming up with, like, you know, how do I decide what like a little bit or a little chunk of charge looks like, right? And then we can kind of add them all up. And so there's several ways to think about this. What I'm going to do is use the most basic little cylindrical chunk. So they kind of look like this. This is a cylindrical little volume element here, right? And I'm gonna call this thing dV. So the amount of charge in this thing. So we're gonna do a little side project over here to figure out how much charge is in this can, in our Gaussian surface. So a little bit of charge is going to be charge per volume times volume. Charge per vol times vol. Or in other words, charge per volume, which is charge density, that's charge per volume, and then the volume is this infinitesimally small thing that we're going to call dV. It's a little chunk of volume. So we need our most primitive volume element in cylindrical coordinates, okay? And so what you want to do is look at like how big each chunk or each side of this thing would be, right? Well, so there's 3 pieces. This is the little wiggle away from the center. And so this little piece is going to have length like dr, right? And then this arc out here, it's a little wiggle and angle. So a mistake people will make sometimes is they'll call this d theta, but d theta wouldn't be a length, so it needs to be like r d theta. So sorry I'm writing small here, but at least I can say it. Sorry, I know this is too small. That says r d theta, okay? So you have dr, r d theta. And then you're going to need a dimension that goes this way. I guess that would be like this edge of it. And I'm just going to call that dl, let's say. Could be dx, doesn't matter. It's just a little excursion along the length of the cylinder. So I'm just going to go ahead and call it dl here. So what that means is dv is going to be the product of these 3 things. So what we've got going on so far is dq equals charge density times, and then it's just the product of these 3 things, r d theta, dr, and dl. Just for style, people usually group the like variables together. So I'm going to say r dr d theta dl. Okay, so that's our little chunk of charge. And now what we need to do is sum them all up, right? So just by logic, total charge is the sum of the little bits of charge. So what we need to do is sum all these things up. Right, so let's do it. Well, we have 3 variables that are changing. So our integral of dq, which is going to be our q enclosed, that is going to be, q enclosed is going to be the sum of the dq's. Got a triple integral coming because you got 3 variables that are changing, right? So we got, here's our triple integral. Let's plug in what rho was. Rho was kr squared. Kr squared times r would be kr cubed. So you got kr cubed. Again, why is it kr cubed? Well, rho itself is kr squared. That's given. And then we have to multiply by another r. This r came along from the volume element, from dv. Right? dv is r dr d theta dl. So there's kr cubed. And then we just finish writing the little wiggles, dr d theta dl. Now let's look at the limits. And this is the part to plug in. This is the essence of like doing these problems, or where people will tend to screw up, is we want the total charge. But total charge inside what? It's always inside your Gaussian surface, okay? So what that means is you want the r integral to run from 0 but to little r, not all the way to big R, because then you'd be calculating the charge on the total charge all the way out, when we just want what's in our Gaussian surface. So it goes from r to little r, or 0 to little r. Theta is, of course, going to go 0 to 2 pi. And then the length, we're just going to go from 0 to L. Okay? So we have Q enclosed equals. So we can quick get this r integral. That function will integrate up to r to the 4th over 4. And then we just have to plug in r and 0. So doing the r integral will give you k r to the 4th over 4. The other thing to notice about that is once you've done that, the other limits of integration on the other integrals, they don't depend on the coordinates. So you can actually separate these out into 3 separate integrals over the respective coordinates. Okay, so this integral over r goes to k r to the 4th over 4. So I'm going to put that down. K r to the 4th over 4. Right. Then you would have an integral over just over d theta from 0. Well, I'll write it down. 0 to 2 pi d theta and 0 to L dl. Right. So this is going to be k r to the 4th over 4. You're just integrating theta, d theta from 0 to 2 pi. So the function 1 d theta integrates to theta evaluated at 2 pi minus 0. So the integral of d theta is just going to be 2 pi. So this is 2 pi. This just means add up all the lengths, along the whole thing. So you're just going to get L. 2 pi L. Right? So the meaning of this expression, that is the total charge. And so we just need to plug that in here. Okay? So we can go back. We've done a little side project now to find the total charge. So let's go back. So we've got E times 2 pi r L equals 1 over epsilon naught, pesky little guy, annoying guy in there. And then let's plug this in. What do we got? Let's see. There's a 2 pi, there's a k, there's an r to the 4th, there's an L, and then, and then there's a 4. Okay, so that's everybody. Yes. Okay. Now what we want to do, let's just cancel out, because all we got to do is solve for E. So if you just divide the 2 pi r L under. Incidentally, though, before I do that, what this is saying is the enclosed charge depends upon r. Well, of course it does. If you make your Gaussian surface as the radius of it increases, you'll be enclosing more and more charge. So the Q enclosed has an r dependence. Okay? And then when you divide this under, you'll see you just reduce that r dependence by one power of r. So you'll divide this under. This r will cancel with this and make this go like r cubed, and the 2 pi's will cancel. And then the other thing that happens, well, all the time is the electric field doesn't care about your imaginary surfaces. So like we made up this thing that was some distance L. Well, that dimension should cancel out because the universe doesn't care about your imaginary surfaces. So L is going to cancel out. You'll see that happen like all the time. And so then we have it. So then we just have to have what has survived. So the strength of the field then is going to be, let's see, we've got in the denominator, we've got a 4 epsilon naught. That's everything that survived down here. And then in the numerator, we've got kr cubed. Yes. Kr cubed over 4 epsilon naught. So this is an expression for the magnitude or the size, the strength of the electric field as you move out. And then if you want to put a direction on it to like vectorize it, what's typically done is people will go, they'll say it's a vector and it points like away, radially away, r hat. So r hat, our unit vector points away. So that is the expression for the field inside. Okay? Well, so the way these problems always go is it says to find the field everywhere. Well, we found it inside, right? When you go to do it outside, you don't have to repeat all this work, all right? What's going to happen when you do the problem outside, on the outside, is your Gaussian surface is just going to extend out here, right? So here's your new Gaussian surface when you go get the field outside. It's way out here, right? You draw a cylinder that's out here. The left-hand side of Gauss's law stays the same. The flux through that Gaussian surface is just E times area perpendicular to the field. Again, the end caps have no flux because there's no field punching this way. It's all radial. And so it's just E times the area of the soup can label. So when you go outside, it's just going to be this. This will be the same, okay? What's going to be different is the amount of charge that's inside. But notice we've already set up a whole bunch of work for this. The only difference is instead of integrating from here just to the edge of our imaginary Gaussian surface when we were inside the can, what we want to do is integrate out so that we capture all the charge, so all the way out to big R, right? Now, a mistake that students will make, and this is really the part to plug in, is kids will integrate all the way out to little r out here. The problem is that they've counted, they would accumulate too much charge because there isn't any charge once you pass capital R here. So if you're going to go get the field outside, and I'm just going to add to the work I've already done here in black. Okay, I'm just going to modify it because we don't have to do too much that's different. This stays the same. This stays exactly the same. We just have to work on what this total charge is. Okay, and so what we want to do is go back to our calculation of total charge, and instead of integrating from 0 to little r, we're going to integrate from 0 to big R. So what that's going to do is make the total charge not dependent on radius anymore. It's going to be a constant. Once you're outside, your Gaussian surface is outside this cylinder, it doesn't matter how big you make it, you've always enclosed the same amount of charge. So all that's going to modify is when this r, the radial integral is done, instead of getting little r to the 4th over 4, you're going to get big R to the 4th over 4. So just modify this. Okay, big R to the 4th over 4. So see, you don't have to repeat all this work. But now this changes the game with the last line. So what we now need to do, and so I've modified the problem now, so we're working on the outside regime. And what I'm going to do is go back and kind of repeat this last line. So the left side of Gauss's law is still going to give us EAperp, E times 2 pi RL. That's the left-hand side. Right-hand side, we still have that 1 over epsilon naught. Okay, but now our enclosed charge does not depend on the radial coordinate. It's just a big constant, right? So it's going to be, I'll just copy that down, K big R to the 4th, 2 pi L over 4. All right, and then we'll divide this under. And what you're going to find out is this is the only place that the radial dependence will come in. The field's going to fall off like 1 over R, right? That's because as your Gaussian surface moves away, you're not accumulating charge anymore. So it's going to start falling off, right? So let's see, the 2 pi's cancel, the L's cancel again. And so then the only thing that really survives from this side or comes over is that 1 over R. So you finally, when the smoke clears, you get the electric field is, well, just all this stuff with an extra factor of 1 over R. So you get K big R to the 4th over 4 epsilon naught, so just a bunch of constants, okay? And then times 1 over R. So it falls off like 1 over R when you're out there. And again, to vectorize it, you could say it's a vector and it points radially away. So to kind of summarize, what we saw was the field when we were inside the cylinder. If you were graphing like field E against radius, right? When we were inside, the field was growing like r cubed because we were accumulating more and more and more charge with our Gaussian surface. So the field strength in here is growing. It goes like r cubed. So a lot of times people read it like this. They'll say it kind of goes like r cubed. And then you get out to the outer surface. And then what happens is your Gaussian surface stops enclosing charge as you go out here. And so then the field's going to start falling like 1 over r. So it's going to fall like 1 over r on the outside. Okay. You can expect this 1 over r dependence with any cylindrical symmetry when you're once you're outside of the cylinder itself. So hopefully that helps. Again, that's a general approach for finding handling Gauss's law with cylindrical symmetry. Takeaway points. Left-hand side of Gauss's law is going to be the easy part because you're going to generally choose a cylindrical Gaussian surface, E times 2 pi r L. Right-hand side is, well, that's where the labor is going to be. It's really calculating how much charge is inside of that little can.